quickly kind of discuss the formulas that are going to be on here that you should know. So obviously you need to know the formula for momentum. Okay. You need to know the impulse momentum theorem. When is this true? Right here.
Net force is 0.
No.
Ah.
Yeah, if the net force is the acting force.
So it's true when what?
When the net force is the acting force, right? The force of impact, or the force that hits the object and makes it accelerate in one direction or another. Let's see. I got. When is this true?
In all collisions and explosions.
If the F net is 0, right?
Oh, for 2.
When is this true? When we do that?
Perfect inelastic.
Elastic.
Just
Okay, so another way to think about kinetic energy is in terms of momentum. So we could put that in that equation. Am I forgetting any of the equations that we used in our momentum section? Ooh, thank you, yes. Center of mass of a particle system. Very good.
Oh, is that going to be on the test?
Yeah.
that's easy.
Yeah, it's easy.
On those problems, you could choose wherever D is, right?
The origin, yeah, you can pick wherever you want that origin to be. Okay, cool. Anything else that I've forgotten? No? Okay. So then we can go ahead and get started on the actual problem. Y'all got all this?
Is there?
Just everything but that last.
All right, that very first question, an Olympic curler releases an 18-kilogram stone with a velocity of 9.7 meters per second. What's the momentum of the stone? That's exceedingly easy. Please figure it out on your own right now. The only way you'll miss this is if you leave it naked or you have no sig figs. Or rather, your sig figs are wrong. What do you get? Okay, 170 kilogram meters per second. Very good. Okay, number 2. A 3.2 kilogram stone is dropped from rest at the top of a 2.2 meter ledge. If the collision of the stone with the ground lasts for 0.60 seconds, what is the force of impact applied to the stone when it strikes the ground? Okay, so there's the ground. Here can be our ledge. Alright. This stone's going to fall off of that ledge, starting from rest. The ledge is 2.2 meters. So it's going to strike the ground. Now, and then it says what? The collision lasts for 0.6 seconds. So the time of the collision is 0.6 seconds. What's the velocity at the beginning of the collision? No.
Oh, beginning of collision.
The velocity. What's the velocity at the beginning of the collision? Were you told the velocity at the beginning of the collision? No. So let's see if we can figure that out. If this stone here drops from rest and it falls this distance and it's in free fall, so what's its acceleration? Negative 9.81 meters per second squared. Can we calculate what the final velocity of the stone is the instant that it begins to touch the ground?
Yes.
Yeah. And the final velocity of the free fall will be equal to the initial velocity of the collision. Right?
Yes.
That makes sense? Okay. What do you think the final velocity of the collision is going to be? 0. Okay? The final velocity of the collision after we're done colliding, now it stops. That's what you guys always wanted to say, right? Final velocity is 0. Now you finally get to say that, okay? The final velocity of the collision will be 0. Okay? So that means I need to find this with kinematics so that I have this so that I can use momentum, right? So what equation, which kinematic equation, given the information that I have, will allow me to solve?
VF equals VO plus 1/2 AT squared?
Nope.
Plus
not.
plus AT.
Nope.
Final velocity.
This time. Is this the time that it takes for the stone to fall?
Yes.
No, that's the collision.
This is the time that it takes for the stone to collide, right? This does not go in your kinematic equation, okay? So we don't have time of fall. So what equation should we use? Okay, so let's see here. Velocity final squared equals velocity initial squared plus 2a times delta y. This goes away. Alright, so 2 times ay, the acceleration of the y-axis, negative 9.81 meters per second squared. Delta y, alright, the displacement of the y-axis, 2.2 meters, but it's falling down, so negative 2.2 meters. And, of course, anytime that you introduce square root, it's plus or minus. And since the stone is falling down, the final velocity needs to be negative, right? Does that make sense to everybody?
Mm-hmm.
Okay, so plug that in your calculator and let's figure out what the final velocity in the y-axis is for the fall.
.56993 meters per second.
Negative.
Yeah, negative.
Got yourself.
Okay, so that final velocity in the y-axis of the fall, we said is going to be equal to the initial velocity for the collision. So now let's see here. They want to know the force applied on the stone, right? Okay, so let's see here. Impulse momentum theorem. Impulse is equal to the change in momentum, which is also equal to the net force times the change in time. And it said, what's the force on the stone? Is the force from the ground on the stone, is that the net force?
Yes.
Yes, so we won't have to do any sign flipping on this. What we get, that's it. Okay? Alright, so let's see here. Do I know the mass of the stone? Did it tell me that?
Mm-hmm.
Yes? Okay. So let's see here. Change in momentum, that's mass times change in velocity. So what is the mass of the stone?
3.2 kilograms.
3.2 kilograms times the final velocity of the stone for the collision is what?
0.
0 minus the initial velocity of the stone. So we're minusing a negative, right? So that's going to be plus this 6.5 number. So that's going to give me my change in momentum, right? Okay? And that is equal to the net force applied, which in this case is the force of the ground acting upward on the stone, times the change in time, which was 0.6 seconds. So what should I do to find this net force?
Divide by 0.6.
Yeah, divide that over there by the 0.6 seconds. What do you get?
35.
35 newtons. Everybody getting that?
Yes.
Alright, a golfer strikes a 45.9 gram golf ball off of a tee. If the ball is given a velocity of 80.4 meters per second as it leaves the tee, how much impulse is applied to the ball by the club if the collision occurred for 0.00043 seconds? What is the force the club applied to the ball? Alright, so let's break this down. First off, they gave me my mass in grams, so what am I going to have to do?
Kilograms.
Get to kilograms. How do I turn grams to kilograms?
Divide by.
Divide by 1,000. Okay, kilo means 1,000, so we're going to have to divide by 1,000. And then it says that that golf club strikes the golf ball off of the tee, right? So what was the initial velocity of the golf ball at the beginning of the collision? 0 meters per second, okay? It's not explicitly, stated, so we need to infer that and write that down, okay? So that means that they gave me a mass of the ball, they gave me an initial velocity of the ball, they said the ball acquires 80.4 meters per second of speed as it leaves. So they gave me a final velocity of the ball. With those three pieces of information, what should I be able to calculate? The change in momentum, which is the same thing as impulse, right? You should be able to get the impulse from that information, right? Now, the next piece of that, if the collision occurred for this long, they gave me some time, right? They're asking me about a force, okay? What am I going to do there? How am I going to get a force?
Divide your impulse by the time.
Yeah, impulse divided by time is going to give me the force only if the force of the club on the ball is the net force. Is that true? Is the force of the club hitting the ball the net force?
Yes.
Yes, it is. So that's true. Alright, so that means you should be able to solve that question without me. Alright, so take a second and see if you can do that.
Mr. Leatherwood.
Yeah.
Okay, so you know on the time how it's like 0.000043?
Uh-huh.
You count those zeros, right? Because it's in front. Like the decimal.
No, man. You're dumb.
Okay.
And you just got
So,
proved wrong on camera.
Sig Fig.
Can't take my
If
joke.
there is a decimal, which side do you start counting on? The left. You find the first non-zero digit. Where is that at? Right here, 4. So you count that and everything that comes after it this way, right? So I got 1, 2 sig figs.
Man.
What did you come up with for our impulse on the ball?
3.69.
3.7.
Okay, 3.7 Newton meters. And what did we come up with for
It
the
is 2.
F net?
11,000 newtons.
I got
no,
8,600.
8,600. Very good.
Wait, okay.
So
How do you find the
the impulse that you should have gotten, right? 3.7 Newton meters, and the
What's all those Newton meters?
Newton seconds. My bad. Thank you. Newton seconds, and then F net is 8,600 newtons.
Can you explain how we got the
Yeah. So let's see here. We're gonna take our impulse momentum theorem, kind of break that up a little bit, right? This is equal to that. That means that 1, 2, 3.
Oh.
And then the final velocity minus the initial velocity. If you do this, you should get this. Okay. Then this right here is this, okay? Of course you want to use the big long decimal number. So you have the seconds equal to, what's up?
Why did we do 2 sig figs for the first answer?
Oh yeah, we shouldn't, that should be 3 sig figs. What does that give me then? 3.69? Yeah.
I told y'all.
But you still got the units wrong anyway, so.
No, I didn't.
You said Newton meters.
No, I didn't.
Yeah, you did.
It's
on
it's
camera.
on camera, son.
Alright, play the footage.
Roll tape. It's okay, I'm gonna edit all of this down anyways and make it look like I was right on along. So. Alright, so then we're going to divide both sides by our time. And then that's what gives us that net force. Cool, cool.
How do you get the Newton seconds? How do you go from kilograms to...
Kilograms times meters per second. That is a Newton second. Because a Newton is mass times acceleration. This meters per second squared, that's acceleration. So newtons times seconds, newtons times seconds. One of these cancels with one of these. That gets me kilogram meters per second. So kilograms times meters per second is the same thing as a Newton second. Alright. Other questions about this one? Alright. So next question number 4. A 35.0 gram bullet moving at 475 meters per second strikes a 2.5 kilogram bag of flour at rest on ice, meaning the coefficient of friction will be 0. The bullet passes through the bag and exits it at 275 meters per second. How fast is the bag of flour moving when the bullet exits? Assume no flour is lost in the system. Alright, so is the force that the bullet applies to the bag of flour the same as the force that the flour applies to the bullet? Yes. That means that F net equals 0, which means what is true?
Conservation of momentum.
Conservation of
Wait,
momentum,
wait, wait.
right?
Why is it equal to 0 again? Or like why?
Because the forces are equal and opposite
Okay.
on that. Alright, so let's see here.
How do you know like equal and opposite? Is that like always gonna happen or?
Wait, so this is a collision, so it's gonna be 0, right?
Yeah.
Okay.
And pretty much all collisions and explosions will have F net equals 0. Okay, so let's see here. I can break this apart so that it's, you know, it would be the two pieces, right? The bullet and the flour, but that flour is doing what in the beginning? Sitting still, so it has no momentum yet, right? So let's just talk about the bullet then. So that's going to be 0.035 kilogram bullet times the initial velocity of the bullet, 475 meters per second, equals, now let's talk about the after, okay? The bullet's now moving at 275 meters per second, so 0.035 kilograms times 275 meters per second, plus, what can we say about the bag? What should we say there?
2.5 times final velocity.
Yeah, 2.5 kilograms times whatever the final velocity of the bag is, right? This term contains the thing I'm looking for, so help me start getting it along. What should I do? Yeah, subtract that over there, right? Now what? How many sig figs should your final answer have? 2. Very good. Okay, who's got it? Ryan, go ahead.
2.8 meters per second.
Okay, Ryan says 2.8 meters per second. Do y'all agree with that?
Yes, sir.
Yeah, okay. And which way?
To the
To
right.
the right.
To the right, okay. Onward we go. Number 6. A 2,200 kilogram vehicle traveling at 26 meters per second can be stopped. What's that mean? Be stopped.
Put to rest.
Is 0?
Yeah, final velocity 0,
That's
right?
what I meant.
Yeah, put to rest. In 3.8 seconds, if the driver slams on the brakes. What is the impulse exerted on the vehicle, right? So, let's first decide, is the force that the brakes apply to the vehicle, is that the net force?
No.
Yes, that's the only thing
No,
stopping.
the road stops it with
Yeah,
friction.
No, we neglect friction in the
Friction is
momentum
right
section,
now.
right?
Put me in
Yeah,
physics
so,
school, man.
yeah, the brakes that are acting on the car are causing the car to decelerate, right? And that, remember, acceleration is proportional to force, right? So if the braking force is that way, the acceleration is that way, that's why the car comes to a stop. The net force acting on the vehicle is the braking force. So we can use the momentum impulse theorem, right? So now let's see here. They give me the mass of the vehicle, they give me the initial velocity of the vehicle. They tell me it's going to come to a stop. That's final velocity, right? So I have initial and final velocity and a mass. What can I get out of that? Yeah, I can get my change in momentum, which is the same thing as the impulse, right? So you should be able to solve for that then. How many sig figs will this have?
2.
2, okay. And since they're asking for impulse and not momentum, what would your units be?
Newton
Newton
second.
seconds.
Newton seconds, very good. Alright, so who's got it? Oscar.
Hey,
57,000 Newton seconds.
I thought you said it was final minus initial.
It's negative.
Negative, yeah.
Oh, whoops.
God.
Good job.
It's hard, Oscar. We all make mistakes.
Bro, that's embarrassing.
Alright, so negative 57,000 Newton seconds, okay? Next question builds off of this one. So in the problem above, what average force is exerted on the vehicle in the stop, right? So what are we going to do here?
Divide the impulse by the time.
Very good. Divide your impulse by the time. Is this the impulse you're going to divide it by? This number exactly right here?
Make it positive.
No, we need it to be the
I'm
big
kidding.
long number, right?
Kidding.
Do not make it positive,
I'm
David.
kidding, I'm kidding. I know I wasn't.
Okay, so what is my F net then?
1,500. 15,000, same thing. That's what I meant, I swear. I swear.
It is a good thing you are.
Good? Okay, so next question, number 8. Consider two carts of masses M and 2M at rest on an air track, meaning there's no friction, okay? So think of like air hockey table kind of a situation. You push each cart for 3 seconds, exerting equal force on each. At the end, the momentum of the light cart, or the lighter mass cart, is what? So A, 1/4 the momentum of the heavy cart, B, 1/2 the momentum of the heavy cart, C, equal to the momentum of the heavy cart, D, twice the momentum, E, 4 times the momentum. What do we think here? And be able to tell me your reasoning why you think that.
I don't think this is right, but
I think it's
change
B.
in momentum equals F net times time. The F nets are the same and the time's the same, so they're equal.
Very good. Yep. Okay, we are applying the same force over the same period of time to both the carts, so the momentum is the same for both of them. The change in momentum is the same.
I like it.
Alright.
Wait, I thought you had to do. I thought this was one of the ones where you do a proportion statement.
That's right.
Oh,
What?
I thought this was
did
one of
not
the ones
see-
where you do a proportion statement.
You could.
I
Can you
did
do
it.
that real quick?
Or which way's like the easiest?
Well, you left out the M times change velocity.
We don't need that right now.
Man,
Here.
thank you, because I know I'm an expanded on the test and they
Okay.
get confused.
And I will too. Alright, so it says you push each cart exerting equal force. At the end, the momentum of the light cart is whatever it is. Okay? So, let's see here. The masses of the carts, right? That's a constant. They don't change while you're pushing them. Okay? It said that the force is equal, so that stays the same. Alright? So, let's see, if I increase the, well no, nothing changes, right? So, the same amounts of time acting on each cart means the cart's going to have the same change in velocity, which we know that's proportional to the change in momentum, so there is no change in
So
momentum.
they honestly all cancel out.
So if they all cancel out, it's equal.
Like,
Yeah.
explain like
Like, okay, since David made me expand this, right? So I can say that the change in momentum is equal to mass times change in velocity, right? Okay, this is constant. That means that change in momentum is proportional to the change in velocity, right? This stays the same here for both of the carts,
why is it proportional there? Just because it is.
because that goes away, and they're both in the numerator.
Oh, okay, yeah, I got it. Sorry.
So the time that I act on both of the carts is the same. The velocity then, or the change in velocity of both the carts would have to be the same over time, right? So if that stays the same, then that has to stay the same. Does that make sense? Like both carts are covering the same amount of distance in the same amount of
So
time.
if it was
they have
like-
the same velocity.
Feels like M and 100 M, and it had that same time, same force, it would just be equal.
Yeah. Next question. A ball bounces off the floor as shown. The direction of the impulse of the ball is what? Alright, so let's see. Ground, ball.
I can't tell if this is like easy or like, you know.
Well, they're all easy, right?
Yeah.
Yeah. So, let's see here. What's the impulse of the ball? Impulse, the same thing as change in momentum, right? Change in momentum, mass times change in velocity. This is acting at an angle, right? That means there's an x component and there's a y component, right? So let's see, the y component would look like this before the collision, and the x component would look like this before the collision, okay? And then after the collision, the y component would look like this, and the x component would look like this, right? In which axis do you notice a change in momentum? The y-axis, right? X-axis stayed the same, okay? Here, the ball hits the ground. This says what's the direction of the impulse, of the ball, right? Acting on the ball. So it was like this, and now it's like this.
Straight up.
So up, right?
Man, but
So it would just, you would
So
just
it
look
should be
at the y component on it?
Well, in this, if it was exactly this
Answer
question.
straight up.
Yeah, so just show you.
So can you give us an example of an X, right? Like,
They do the same
Yeah,
thing,
I
but
did
sideways.
ping pong paddle hitting a ping pong ball out of your notes.
Just flip the
remember
paper
that
like
one?
this.
Let's see here. This was our ping pong paddle right here, right? And the ping pong ball came in and hit the paddle like this, and then took off that way, right? And it acted at this angle of theta. Do you remember this problem? Okay, so we had an x component pointing this way before the collision, and the y component pointed up before the collision. After the collision, the x component went this way, and the y component went this way. The y's are both pointing up, so no change in momentum there, right? Of course, so long as this theta is the same. And then here, the x one went like this to begin with, and then it went like that afterwards, right? Change in direction, change in velocity means change in momentum, right? Okay, the next one. Consider two carts of masses m and 2m at rest on an air track and connected by a compressed spring. After releasing the two carts, the spring expands to its equilibrium point and drops straight down. What is the total momentum of the system composed of the two carts after they are released? Alright, so let's see here. Let me switch to this other marker. So I have one cart connected to another cart by this spring here, and I'm holding those two carts together, right, so that the spring stays compressed. And then I'm going to let go, right? And then those carts are going to move apart from each other. Okay, so what was the initial momentum at the beginning of this for the carts?
0.
0, because I didn't let them move, right? Okay, so what must, if momentum is conserved, what must the momentum be after this explosion?
0.
0. Alright. The force versus time graph below represents the force acting on a car that is accelerating from rest at a red light. Calculate the impulse that is acting on the car during the first 5.78 seconds if the force of the car steadily increases from 0 newtons to 3,012 newtons over this time interval. If the mass of the car is 1,500 kilograms, also determine the final velocity of the car. Okay, so you got a force versus time graph, and I think it said something about impulse, right? What should you do? Yeah, do your area under the curve, right? So let's see, that's 1/2 base times the height. So our impulse then is going to be the 3,012 times the 5.78 seconds divided by 2, 1/2 base times height. How many sig figs do we want?
3.
3, very good.
So impulse equals area under the curve for a force versus time graph.
We wrote that down at the beginning of this when we listed all the equations. So what do we get there?
7,530.
8,000 what?
700.
What? It's 7,530.
What are you doing?
You can't mess up this.
Is that right? Is that what y'all got? Or is
No,
David wrong?
David's wrong.
No, it's not 8,000. It's 7,530.
No,
Eight thousand.
So what is it then? Like
Oh, I didn't add the 0.78.
oh,
Oh.
okay. 8,700 Newton seconds.
I thought it had to be 3 sig figs.
It does.
Yeah.
God. So
It's, the actual
don't
number-
round that. So what is it?
Well, it's
8,704.
So you could do 8.70.
Well that's not. If you
Wait,
do
but isn't
that,
it-
That's 4. So
Isn't it
yeah,
8, 7?
that'd be
You could
4
do-
sig
No,
figs.
8
It'd be
point
5.
times
Wait,
5, wouldn't it?
0 times 10 to the third.
Wait.
so
Yeah, it would be
much.
5.
Wouldn't it be? I think it'd be 8,705.
No,
Yeah.
but that's
Well,
still 4.
It doesn't
Ours is
matter.
0.
We need this to be in scientific notation.
Oh, okay.
No, she's talking about the top one.
Okay, never mind.
David, what happened
Right.
to you? You can't be getting this wrong.
Hey, shut up. I don't know how. Okay, I'm done.
So are we
And explain, like, this is kind of like a stupid question, but I get confused when you're like switching over to scientific notation.
Alright, the decimal, when it's not shown, is always at the end. When you're going to turn something into scientific notation, you must move the decimal behind the first significant digit. 1, 2, 3. So we say 8.70, that gives me my 3 sig figs, times 10 to the, how many times did I move it?
Okay, thank you.
Alright, now let's see here. The next one, given the mass, what is the final velocity of the car, right? Okay, so what am I going to do here?
Divided by mass.
Mass times delta. Change in velocity.
Okay, so we know that the impulse is equal to the change in momentum, which is the mass times the change in velocity, which is the mass times the final velocity minus the initial velocity. Okay, we just found out what our impulse is, although you should use the full number, not the rounded version. Okay, they gave us the mass. They said that the car is accelerating from rest, meaning the initial one here is 0, right? So yeah, we'll divide our impulse by the mass. That should give me the final velocity.
Is it still 3 sig figs?
Well, I would say so, because this right here is
There's
what
2
led
sig
me to
figs.
that.
The
It's
mass
2 sig
Oh, the mass is only 2, so then yeah.
Yeah.
8704668.
I have a question.
Alright,
Why
what
did
is
you
it?
do 7
Not
and
funny.
4.68? Why didn't we put
I
5?
actually have to go now. So.
Why didn't we put 5
I gotta go now, so I ended on good.
Because
Because it doesn't matter. This is 1, 2, 3. This is the third sig fig. I don't care what comes after that. Okay, so what do you get for your final velocity then?
5.8.
meters per second.
Very good. 5.8 meters per second.